The webinar is part of our custom tool development strategies for chiplet reliability. It's the second webinar of our series. And to give you briefly the agenda, we will have an introduction to inform you about our webinar series. So we have our next topic will be the CoMeT interval thermal simulator for 3D ICs from Dr. Anuj Pathania. The next topic will be the physical hierarchy exploration of 3D ICs from Professor Alberto Garcia-Ortiz. And the third will be PROTON physics-based electromigration assessment on modern VLSI power grids from Dr. Olympia Axelou. And then we will have a Q&A section. So to give you a brief overview, COIN-3D is organizing a webinar series. The goal of COIN-3D is to exploit the research and knowledge exchange in the 3D VLSI domain. So we plan to do a lot of activities like summer schools, webinars, and advanced courses. So we have our first webinar also on our YouTube channel about machine learning application in NDA for chiplet reliability. And now we're in our second webinar in the custom tool development strategies for chiplet reliability. And in about 8 months from now, we will organize our third and last webinar about reliability assessment in emerging technologies for 2.3D chiplets.
Okay, so thank you, George. So I'm going to talk about the CoMeT simulator, which we are building in the University of Amsterdam. So I want to start with a little bit saying about myself. So I'm Dr. Anuj Pathania. I am from New Delhi, India, and I did my doctorate from Karlsruhe Institute of Technology in Germany. And I specialize in the area of computer systems with focus on low power design, embedded system, and electronic design automation. And I have been with University of Amsterdam for now last 4.5 years as an assistant professor. So I'm going to start by talking about von Neumann architecture. So almost all the computers you see today are of von Neumann architecture, where they have 3 parts. One is in an input out device and an output device, and these devices are connected using a processing unit, which can be of different types, but basically is bifurcated into 2 parts, one for processing and one for memory. So the processing is where your computations happen, and memory is where your data is stored. And von Neumann architecture basically allows for a separation between the processing and the memory, and the data gets transferred in and out from the memory to be processed in the processing unit. So that is what von Neumann architecture is. So this is how von Neumann architecture is realized in a 2D processor. So mainly the main memory and the CPU, they are separate and they're connected using an interconnect using the motherboard. So almost all processor designs from before recent years used to follow this particular design. So the problem with this particular design is that first, the bandwidth of the interconnect is limited. So there's only so much data that can be transferred between the CPU and the main memory. And also the CPU and main memory are also very far away. So this leads to a lot higher data latency than what we want. So, but if you look at today's high-end applications, whether we're talking about gaming, whether we are talking about AI-based image speech recognition or generative AI or virtual reality and augmented reality or high-def videos, if you want to do all these computations on chip, one of the main bottleneck here is that all these applications are highly memory intensive. So that means that they require a lot of data to be moved in between memory and compute in it for it to work. And then the computation itself does not become the bottleneck, but the memory bandwidth kind of becomes a bottleneck. So we can't run our CPU or the processing unit as fast as we would like them to run because we cannot feed them enough data. So to address this problem, which is also called the memory I/O bottleneck or the memory wall, new designs for non-von Neumann architectures were proposed. So to break this memory wall, basically what we have done in a processor design is to move from a 2D processor to a 3D processor design, whereas previously logic and memory were kept separate and connected using a PCB substrate interconnect. We first overlapped memory chiplets on top of each other to create a high bandwidth memory or hypercube memory, which greatly increased our capacity of our memory, but didn't solve the bandwidth or the latency problem. So what we did was that we, in a 2.5D processor, which is now everywhere, for example, all the latest processors from Apple Silicon use a 2.5D processor design, that the logic and memory were put together into the same package using interposer. Consequently, the latency went down and the bandwidth increased. And the final piece of the puzzle that was left to do was to stack the memory directly on top of the logic, which allows for 3D interconnect connections between the memory and the logic, allowing for a massive increase in the bandwidth and very low latency. But this came with some undesirable consequences, which basically came in terms of heat. And if you are doing high performance computation, whether it's in mobile, desktop, or cloud, heat is your number one problem, because if you do not dissipate the heat, your chip will get damaged, and it has severe reliability consequences for your chip. So heat has to be taken away. In embedded form factor, that heat is especially difficult to take away, because we can't really put a fan on your mobile devices and so on because of the given form factor. The problem is that the 3D design make this worse. So what happened was with the 3D design is that you are putting the memory and the core and logic directly on top of each other, which increases, which causes the which you send the power for both the memory and the logic to the same die, to the same silicon, but the surface area which you can dissipate the heat is severely reduced, because now you do not have the same amount of surface area while your volume has increased. So this kind of traps the heat in between the chip, which makes the thermal problem much worse and makes our chips much more less reliable than before in case of 2D processors. So heat is fundamentally very bad for reliability of processors. When we're talking about the reliability, we talk about basically two kinds of reliability. One is hard reliability and one is soft reliability. So hard reliability basically means that heat or due to computations, the transistors themselves physically start to break down until a point is reached where they cannot operate normally. So this leads to a permanent failure in the chip, and your processor or your memory kind of dies. And this is irreversible. On the other hand, we have soft reliability, in which what happens is that your processor, your transistor is stuck by a high energy particle, which kinds of shorts your transistor, which can lead to temporary transient errors. And these particles can come from outer space, and or this can come from the radioactive decay in the chip itself. And these particles are always hitting, but temperature kinds of make this problem worse, because higher the temperature is, higher is the electron mobility within your transistor, and consequently they become more susceptible to soft errors, and soft reliability of your processor goes down. So if you want to study reliability, what you have to do is that you have to first study thermals of a processor, because the temperature and the reliability are so interlinked with each other. So a lot of processors or embedded boards have thermal sensors in them, which actually can be used to do thermal research and maybe also for reliability research. But one of the main problems which we see with real world th thermal research is that the sensors on the real processors, they do not have very high resolution in terms of spatially or temporally, which basically means that maybe there is only one thermal sensor somewhere on the processor which cannot capture the hotspot forming all over the processor. Uh, so it does not have the spatial resolution, and temporal resolution means that because the chip is physically itself is very small, the temperature moves very fast on the chip, and these sensors, if they update at a very low resolution, let's say once every second, then you're going to miss most of the thermal activity on your processor. So that's why the most common way to study thermal research and reliability, thermal research, is to use thermal simulators. Also, it is very difficult to do reliability research on real processors because reliability is a long-term phenomena. So it takes years or nearly half a decade or maybe even a decade for a chip to really break down where it shows a significant wear down. And of course, we cannot wait so long on a real processor to slowly break down. So we need to perform some kind of time warping to accelerate the reliability research. So that's why it's also very difficult to study reliability in a real processors. So the solution to this problem is to use thermal-based reliability simulations. And this is where our tool comes in. So what our tool basically does is that it connects several tools together. It's called CoMeT, and it's a tool chain which connects Sniper simulator with MacPat and Cacti power simulators and hotspot thermal simulator. And what you can do with this is that you can create schedulers which you can use to study thermal and reliability scheduling, and you can run real workloads. Means you can run x86 binaries on top of this tool chain, and then you can also accelerate time, and you can study the effect of your system decisions, such as one taken by your scheduler, on the overall reliability and the overall thermal properties of your processor. And all of this is open source, and the tool is being actively developed and used worldwide. So you can go on GitHub and download it. So this is how the simulation of the thermal looks like in this chip, in this simulator. So as you can see that this is a parsec benchmark binary running on a processor, and as you can see, the heatsink is on the top, and there are several layers of core or logic, and there are several layers of memory. And what is happening is that since heatsink is with the cores, even the cores produce more heat, they are much cooler. But on the other side, there is the PCB and there is no heat sink, and the heat is getting trapped by the memory layers, which are acting as a sponge. And heat is also very bad, especially bad for memory, because the data in the memory can get corrupted because of the heat itself. So this is something what is being produced in real time by the simulator as an output.
Perfect. So welcome to this second presentation. The topic of this presentation is a hierarchical 3D design exploration mechanism that we have developed. Let me start by trying to acknowledge the complete team that has been working in this project. On the one side, we have the Georgia technology led by Songkun Leung in the direction of EDA for 3D, also the support of IMEC, especially from Frankie Cator and Maurice Brunion in terms of the technology, then collaboration with the ETH Zurich, the group of Luca Benini regarding the mempool hardware, and finally our group at the University of Bremen, working again in 3D design. Let me start with one short motivation. Let's consider that we want to implement a complex update system, like for example, the mempool. Mempool is composed in one of the constellations by 4 groups of 16 tiles. When we check what is in every group, you will see that this group is composed by 16 tiles of multi-core processors with some local interconnect, and then one additional connections in the north and the east with the other tiles. If we now zoom into the tile, you will see that the tile is a complex 4-core system with L0 cache, L1 cache, interconnect, shared memory, and so on and so forth. If we want to implement this system in 2D, probably we will subdivide it in small blocks, and we will independently synthesize and perform the physical implementation of the different sub-blocks in a hierarchical way. Once we have implemented, for example, the tile, we will integrate the tile into the group, and finally we will integrate the group into the final system. We just traverse the hierarchy from the bottom to the top. This methodology is perfectly well established in 2D. However, when we want to implement such a complex system in 3D, we will find dramatical difficulties. So fundamentally, the goal of this short seminar is just to introduce one mechanism to allow to use 3D physical implementation in this scenario. But let me first review which are the benefits and the difficulties of this hierarchical approach. In terms of the benefits, we see that we can address very large designs, like for example the memory that we have discussed before, with an acceptable runtime, even if we have system with maybe 128 cores. We can reduce identical blocks. This was completely clear in the previous example, where we have a multi-core example. Also, in commercial environment, it is of great importance that we can concurrent work with different teams, with different persons in the same project. So maybe we have some implementation in the NOC, another one in the course, and so on. And finally, another big advantage of the hierarchical methodology is that we can elegantly implement third-party intellectual property blocks. All these 4 aspects play a key role, especially when we want to do an easy design exploration. If we want to see what happens when you change the number of tiles that we have in the group, for example, or if we change the area, which are the implications in the final layout. However, this hierarchical approach has 2 fundamental problems. The first one is that we require a careful budgeting of the different blocks, especially in terms of timing constraints. And second, that we also have to define very precisely the physical constraints for the different hierarchical parts. In the domain of 2D, we have some tools which are helping us in this regard, but again, in 3D, there is almost no tool for doing this. In the next slide, I would like to summarize which is the state of the art in terms of flows for 3D. Fundamentally, the 2 more, let's say, important ones are sequential 2D and macro 3D. And what we would like to present today, we want to discuss today, is a new hierarchical 3D flow. The key idea of the sequential 2D is basically to use a partition so that we can implement our design in 2 separate dies which are separated. In macro 3D, the key idea is that we can try to implement a system using a memory on logic approach, but using a holistic view so that we can see the complete metal stack. These 2 methodologies present some advantages and disadvantages. For example, in terms of sequential 2D, the fact that we can have a very free partitioning is a very plus, while it has some negative aspects, like for example, that we need to perform a partition which typically is very, very difficult to do at the first. On the other hand, Macro 3D has some advantages in terms of using all the, let's say, possibilities of the routing simultaneously in the 3 dies, while it has some limitations since it is mainly focuses in memory and logic. What we would like to do is to try to combine the advantages of every one of these approach so that we can get no restrictions in terms of the partitioning, that we can get a holistic routing approach like in Memory 3D, and that we can also use the space that we have in the different dies to the maximum. Before we start with the explanation, let me try to summarize again these strengths and limitations of the existing flows. As said, one of the strengths of the sequential 2D approach, what you can find today in Cadence, is that we have no restriction for the partitioning that provides a high flexibility. However, we need the critical partitioning step, a complex modeling of timing constraints, and probably the key problem is that when we are routing, we cannot reuse the backend of line of the different tiers at the same time. If now we compare that with Macro 3D, you will see that the fundamental strength is that we have a complete view of the timing constraints and the bucket of line so that we can use metal. In this sense, we can provide a full place and route with a complete optimization using, for example, incremental synthesis while the place and route. However, we have two important limitations. First is that this approach is limited to cases where we have large IPs, like for example, when we are working with memory and logic. And also that it is very common, if the two tiers are not perfectly 50%, that some area in some of the tiers will be waste. Our solution for that is hierarchical 3D flow. In order to understand hierarchical 3D, I think it will be worthy first to have a look to the Macro 3D overview. Here you have, in a short slide, hopefully you can see it, the key idea of Macro 3D. On the right side, you see which are the elements that we need to be able to execute these in terms of the creation of a full pattern of line and the creation of IPs. In the left side, you can see the steps. Fundamentally, if we make a zoom, if we try to have a look about which are the requirements, you will see that the fundamental idea of Macro 3D is that we start with two separate tiers and we want to combine them into a single full stack backend of line. These, for example, can be done combining the lab files of the two technologies, allows the tool simultaneously to have a look to the complete stack. Yeah. If we make a zoom to the second part, you will see that when we are doing the routing, in fact, we can combine metallization between these two tiers. The next step that we need to execute this flow is the generation of dedicated IPs. If we, for example, think in terms of the implementation of memory elements in the top tier, you will see that by implementing there, the location of the pins is not going to be in the original Metal 3, but in another layer according to the F2F full BEOL. This is what we call here M3MD. So we need one step where we adapt all the IPs that we are going to use into the, let's say, die where they belong. Good. So here you have seen these two parts, creation, full BEOL, and create the IP. If now we move to the right side, so the steps, the fundamental steps that we have is first the flow planning, where we try to define what should go to the top die, what should go to the second one. Then we have the 2D projection step, where we project the pins of the top die into the lower one. Then the next step is the complete place and route and sign off of the bottom tier, just using a standard 2D methodologies. And finally, when we have this place and route, we can proceed with the last step where we have to separate the combine stacks into those so that we have the top tier and the bottom tier independently. Again, let me have a look to this step with more detail. Here we have the step corresponding to the floor plan. You can see that when we are working in the bottom die, we can locate some macros with the normal pins without any restriction. When we are locating macros in the top die, this macro we leave in the additional left tiers that we have developed before, while the pins are going to be projected. Here you see this small red square from the top tier to the bottom tier. Once we have this substrate, you notice that to make sure that the tool can understand that, the trick that we are going to use is to have one virtual macro that occupies fundamentally the size of a standard cell and that has pins projected into the place where actually belong to the lag macro. Once we have this system, we can proceed to the normal place and route. Observe that in this step, the complete place and route is done completely with the standard 2D tools. The tool sees the complete stack of metals because we have extended LF files. The tool can change the location and the size of the standard cells. We can floor planning automatically all the macros that we have in the lower part. The only limitation that we have is that the location of the macros which are in the upper part is fixed. The two advantages that you get with that is that we have a perfect definition of the timing and also that we can use the complete stack for the metallization even if we are using a standard 2D tool. With this idea in mind, now we can try to address how can we extend this macro 3D tool to cover more complex scenarios. The fundamental idea is to try to combine the advantages of sequential 3D in terms of floor planning, freedom for the partition, and macro 3D in terms of seeing the complete style flow. And for that, what we are going to use is a bottom-up hierarchical approach where we decompose our implementation problem in different cycles of iterations. Probably it is easier to see that if we have a concrete example. Let's imagine that again, we want to implement the mempool. So the first thing that we are going to do is to define our hierarchy, our steps. In this case, they are pretty clear just by the definition of the hierarchy in the design. So we have the tile, the group, and then the complete system with the 4 groups. Then we start with implementation of the core. This is what you see in the small graph in the upper part, in the small image in the upper part. Here we have used an approach similar to macro 3D, where we have decided to place the large L1 cache in the top tier, while in the bottom tier we are placing the standard logic cells for the design, but also the 4 L0 macros. Note that since the system is asymmetric, so the area of the bottom tier is larger, we are reserving some area in the top tier that we will reclaim in the following iterations. Also, you see that there is a couple of small green points. These are some areas that we are reserving already so that later on the implementation of the system is easier in following iterations. Once we have this partition with this step reserved, we can adjust the normal flow that we have seen before to complete the tile. Once we have the tile, we can create the group. For that, conceptually, we just have to integrate these 16 tiles and to add the logic for the log interconnect and for the node. Note that we can do this just by swapping the concept of what is the working tier, what is the tier where it is fixed, so that in this iteration, the complete tile is seen as an IP, only occupying the part where the standard cells and the L1 memory is located. In this iteration, all the blue areas that actually are in the top tier will be used for routing, for generating the local interconnects and the logic of the group. Just a small detail, even if right now we are working in the top tier, because the tools need to see the stack in the proper way, actually what we are doing is to flip everything so that the tool believes that the top tier is actually the only tier where we have standard cells. Again, there is some asymmetry between the top and the bottom tier so that we have one space that we can reserve for the next iteration. In the next iteration, we just connect the different groups together, and now our design is fundamentally similar, our flow is fundamentally similar to the macro 3D, where again, we are just placing the standard cells in the bottom tier, in the regions which are in green. Notice that when we are in this step, there are some areas that we reserve already in the tile with green areas that it can be reused right now. This allows a great flexibility in terms of the location of the buffers when we are generating the complete system. Yeah. You see that the fundamental idea is that we are doing a kind of partitioning, and that in each iteration, we are just using the full methodology of macro 3D. In the next slide, I'm showing with a bit more detail exactly how the procedure is working. I think we just have a couple of minutes, so let me go relatively fast on that. What you show in the left is actually the location of the top and bottom tiers, for example, when we are working in the first step. You see that in the bottom tiers, we have our standard rows for cells. We are placing in one cell, which actually is the size of our standard cells, but that represents the complete memory that is going to be located in the upper layer. As we place this element, the pins of the memory are propagated to the bottom tier. These are the yellow elements that you see there. In addition to that, you see that we need to define some blue pins. These are the connections of the tiers with the next levels. And finally, you can also see in gray that we are reserving some space that can be used for the different elements. Once we have defined this flow plan, we can just run the normal methodology. And as you can see in the section in the middle, we can do the normal routing. We just see additional vias in the F2F layer, and we can just use all the meta layers in our design, both the layers that we have in the bottom tier, but also the layers that we have in the top tier. The tool realized that he needs to do a connection to the memory macro. Even if he does not see the memory macro per se, he just sees one obstruction. Once we have done the implementation of this part and we go to the next iteration, then we have to work on the top tier. And as I said, this is the point where we have to do the stack inversion. We just rename what is the metal 1, metal 2, what is the standard cells in such a way that now the place and route tools believe that he's just working in one of the tiers. Note that when we do that, we have to change automatically all the interconnects that we have done before into obstructions. We have to replace the location of the memory macro with one overlap and one construction. And after doing that, we can proceed with the normal place and route. By iterating with this stack inversion in different layers, we can complete the implementation of our chip. Yeah. So summarizing, you see that fundamentally what we are using is a bottom-up hierarchical implementation approach, where we are reusing the assigned area that we have reserved so that we can minimize our constraints. We are working fundamentally in a multi-tier approach, and because of this ping-pong approach between the different tiers, we can in fact place cells in both dies. This greatly expands the possibilities for 3D design and also the design exploration. If we want to implement completely that, let's say, the rough idea that I described right now, you see that some of the elements that we need is first a RTL clustering approach in such a way that we can cut our design in different steps. We want a logic-on-logic floor planning approach that we have to do at the very beginning. And also, we require a holistic approach for the 3D physical implementation that we are implementing using Macro 3D. In order to enhance the methodology, it is also possible to add one automatic floor planning step, and also it's possible to add some improvement in terms of the definition of what is white space, so that we can get a trade-off between the possibilities of recovering the space that we have in different iterations without having to create a much detailed left file. Slide, you have the complete flow that we have in hierarchical 3D. You just see that we start with hierarchical partitioning, then we can start with implementation of every block, then we do the 2D synthesis using the standard PDK with the additional definition of methodologies and the IPs with extension. Then we can do the 3D floor planning with budgeting, placement, and legalization. Out of that, we generate the complete 3D netlist, and we can do the full placement route. Once we have seen one iteration, we can abstract this step, generating a detailed left and lib file of our block. Then we feed back to the stacking version, we change the design, and we continue iterating. Once we have completed all the iterations, we can just proceed with the full chip assembly and the final GDS. I said there are two steps that can be used to enhance this approach. The first one is the clustering approach. Basically, what we are doing here is to analyze our netlist and to try to see which are the different blocks that we can combine into one single cluster in such a way that the floor plan later on and the distribution between the different tiers is even easier. Fundamentally, this is a clustering approach. I think it's not worth it to go exactly to the details of the algorithm. The second enhancement is actually the automated floor planning. Shortly, what we are doing is first we start with a Fiducia-Matthews partitioning, where we cut the netlist into different parts which are related with what we want to place in the bottom and the tier. With this initial partitioning, we fix it, and then we start to analyze the assignment into the 3D part using just a 3D sequence per generation. These steps are very similar to the steps that you will find in any sequential 2D methodology. After doing that, we will unfix the partitioning, and then we will start a simulating annealing approach, where we try to improve the location of the elements and the macro. After this initial simulating annealing approach, we will fix the macros and the outlines, and then we will continue with another simulated annealing, where we try to determine the complete location of the elements. Once we have the floor plan, we can automatically perform some assignment of the vertical interconnects of the MIVs, or the face-to-face interconnect to the layer. And for doing that, fundamentally what we are using is assignment that try to minimize the distance using a bipartition approach. In the cases where we are using face-to-face approaches with a large path, it is normally require a legalization approach and to keep out of zone distances so that we have few violations. In this slide, we just have a summary of the result. Here we are comparing for mempool, actually for the full cluster, which are the results that you can get with 2D, with the sequential 3D, with macro 3D, and with a hierarchical. You see first that obviously macro 3D have some advantages versus sequential 2D because of the possibilities of a perfect location of the macros, but nevertheless it weighs some area that actually is recovered by hierarchical 3D, so that we can get an area 0.65 that is dramatically smaller than what you will get with sequential 2D or macro 3D. Also, because of the clever use of area, you see that actually we get a huge improvement in terms of the effective frequency. In particular, in the cluster, we have a high density of interconnects that were limiting the speed of the system. And by reducing the space that we have between the tiles, you can see that we can get a much better result. So that finally the die cost is much smaller, and also we get a power delay performance which is almost double what you could get with other methodologies. In this slide, you can see just graphically the result of the place and route of the mempool. Here you have the 2D approach with the tiles, and you see that there is quite a lot of congested area. Then the results that you will get with the sequential 2D or macro 3D, they are quite similar. You can see that we have tiles in the bottom and memories in the top. You can see that because of the use of the macro 3D approach, most of the top tile is completely unused, and because of that, we have a higher area and more congestion in the bottom tile. And finally, in the lower part of the slide, you can see the bottom and top tiers with the hierarchical 3 methodology, where you can see that the tiles are placed much close, and how in the top tier, there is actually a lot of cells which are used for doing the connection, and because of that, we can reduce the area and improve timing. We have repeated experiments with Cortex, where we have 4 cores with an L2, and again, you can observe the same results. We can also analyze GPU like the Mali G52, again, 2 different cores, logic in the bottom and the top, the results are the same. By using this hierarchical methodology, we can get huge improvement. So with this, maybe I can conclude. Fundamentally, what we have presented is just the possibility of doing a full chip R2L2 GDS physical implementation using a hierarchical approach for 3D that is able to explore the hierarchy that we have in our design. It is based on the idea of cutting our design from bottom to top, where we are reusing all the unsigned area and exploiting all the tiers that we have. With this, I can conclude this small part of my presentation. So thank you very much for the attention.
Okay, so hello also everyone from my side. My name is Olympia Axelou, and I am very excited to talk to you today about our in-house tool called PROTON. It is a physics-based electromigration assessment tool for modern VLSI power grids. We will discuss a bit its core principles, the innovative methodologies that includes inside, and how we envision adapting it for 2.5 3D chiplet-based designs. First, let us explain what actually electromigration is. As the current flows in wire, and we are talking about lots of current, the momentum of the electrons drives metal atoms from the cathode towards the anode in the direction of electron flow. Because of this, the cathode gets depleted of metal atoms and tensile stress gets built up, thus voids are created there, while migrating atoms get accumulated at the anode terminal of the wire and compressive stress is created there. Now, the derivative problem is that the resulting concentration gradient that exists due to the stress, the electromigration stress, when it reaches a critical level, it can lead to HELOX and denser material, as we see here in the anode, as well as the creation of voids and consequently to open circuits. And this is the most important part. The phenomenon of electromigration actually intensifies due to the continuous downscaling of the integrated circuits and the simultaneous increase in currents that flow in the interconnects of the lines. It is considered a major concern for nanometer scaled integrated circuits, especially in modern technology nodes in which process variation actually affects the shape. Now, because of its importance on the chip's lifetime, electromigration reliability analysis has already been included in integrated circuit design flow, although the methods used are too conservative for the modern power grid networks and are based on heuristic models. In particular, there are various industrial tools that perform electromigration analysis, such as Voltus by Cadence, RedHawk by ANSYS, which is integrated into IC compiler, and also COMSOL Multiphysics, which is a FEM simulation software package for various physics and engineering applications. Now, the problem is that all these tools although they offer a bundle of analysis, none of them is actually explicitly for electromigration and how it involves in modern power grids and designs. Also, they make use of Black's equations, which is a mathematical model that calculates the mean time to failure of a semiconductor circuit due to electromigration. And it is an empirical method. It is actually heuristic, and now it is often inaccurate for modern integrated circuits. And last but certainly not least, all these tools are closed source software, and the user needs to pay in order to get access to them. However, the EDA community has shifted its focus to open source and embracing initiatives such as open source software strategy by European Commission, and along with other large-scale EDA projects like Open Road in the US. Proton actually aligns perfectly with this action, which can enable smaller design teams and individuals to benefit from cutting-edge electromigration analysis, fostering this way innovation and collaboration within the EDA community. It's actually something very needed. Now, having said all that, we present Proton, an electromigration analysis tool for power grid lines that is designed to be fast and efficient. It actually leverages parallelization and optimized algorithms to handle large-scale power grids. It is an open source and cross-platform EDA tool with intuitive graphical user interface and an easy command line version, which makes it very versatile for any power grid design flow. Now, let's proceed to what is actually in the core of the tool. For accurate electromigration stress analysis, in the core of the tool, we employ the physics-based equation proposed by Korhonen. It is a partial differential equation that models the diffusion of electromigration stress inside a line or an interconnect. And accompanied by the suitable boundary conditions, then we create, and using the FDM discretization, we result to this system here, this ODE system here of size n, which is actually the discretization points. Now, Proton offers two key functionalities. First, it can perform line analysis, which is very fast, a semi-analytical method, in order to calculate directly electromigration stress on power grid lines at a specific time. It keeps the time continuous and takes advantage of the specific form of matrix A, the diagonal matrix A, and performs discrete cosine transform type 2, which reduces the complexity of the calculation from n squared to n log n. Now, on top of that, this method is completely parallelizable for the different lines in a power grid. So this enables the use of multiple threads for complete power grid EM analysis. And now, if we want to specifically calculate and see the transient analysis of transient response of a specific point, we have the point analysis, in which Proton calculates the specific transient analysis of a specific point. And here, in order to do that efficiently, beginning from this state space model that our tool has, we employ an EKS, extended Krylov subspace model order reduction method, in order to lower the complexity of the system by projecting it to a much lower dimension subspace. For this purpose, it leverages the fact that the stress is proved to be more pronounced in the vias and endpoints. So our tool focuses on this point, but it is not limited only to them. So both core methods have low complexity, and thus they are very efficient. And because of the nature of the methodologies, they also are robust and provide accurate results with minimal error. So the Proton core technology was implemented on C++, providing the computational power needed to efficiently perform complex matrix manipulation tasks. For this purpose, Proton, of course, utilizes Eigen, which is a powerful C++ library for linear algebra operations, and which actually provides a specific module called sparse that allows efficient storage and manipulation of very large sparse data structures. And this allows us to handle large-scale benchmarks and accurately and efficiently while having low memory footprint. We further enhanced our tools by linking Eigen to Intel MKL, a highly optimized numerical library that is designed to take advantage of the specific Intel processor's advanced feature, such as vectorization, parallelism, and instruction set optimizations. This means that AGEN, along with Intel MKL, can achieve significant speedups in sparse matrix operations. Also, these two libraries are accompanied by C++ library collection called Boost in order to further enhance the functionality and the performance of the application. Now, for the line analysis and the efficient formation of the analytical solution, Proton leverages the state-of-the-art FFTW library to perform the DCT type 2 transformation required for the analysis. The library is actually widely recognized as one of the fastest and most optimized solutions for performing fast Fourier transfer, ensuring that Proton can perform line analysis quickly and effectively. On top of that, it also uses OpenMP in order to leverage the parallelizability of the line analysis algorithm, which enables us to perform fast, complete power grid analysis. Now, as for the Bayes transient analysis, the internal steps utilize Paradiso Solver, a highly optimized and widely used direct solver for large-scale sparse linear systems. The solver ensures robust performance, which results to reliable solutions and efficient memory usage, something very important for the EDA tools. So as a result, the methods that are incorporated into Proton, along with the libraries used for their implementation, make Proton an excellent choice for efficient and trustworthy EM analysis that is applicable to all power grid sizes while offering robust analysis. Now, having discussed the underlying internal components that form the core of Proton, we will now shift our focus to a broader perspective in order to analyze the proposed tool on a more complete manner, let's say. So, to do that, this is the flowchart of Proton. First, we have the parsing stage, where Proton receives the power grid design in SPICE format. Then, once the power grid design has been received, Proton communicates with an external circuit simulator in order to obtain the currents flowing through its line. It can be any industry standard or open source SPICE simulator, which makes Proton actually easily integrated into any physical design of states. Then, it parses the SPICE file and extracts all the lines of different nets and layers. And then it generates some general NDM-related statistics on the power grid, as well as the complete set of the extracted lines. After selecting the line and the desired configuration, for example, technology, temperature, the width of the line, etc., it discretizes the line with using finite difference method. Then, depending on the analysis, as explained above, the user can choose between the two previously discussed analyses that are integrated inside Proton. And finally, of course, the users can plot and extract the results. And as we said, the primary goal of Proton is to be compatible with typical industrial design flows. This is actually guaranteed by the use of the widely accepted SPICE format for power grid design. For the parasitics. Also, we are always in sync with the present industrial design methodologies and commercial EDA tools as we integrate in the flow of our tool external circuit simulators like HSPICE by Synopsys and Spectrum by Cadence. This makes it very easily integrated into any power grid design flow. And finally, as can be seen, our tool has been implemented in such a way that it's offered a great level of automation that makes it very friendly, user-friendly and intuitive. Now, in this context, the user interface of Proton is designed in a minimalistic way using the PyQt5 library of Python. By diving a bit into the user interface, we have the following components. First, at the bottom left, we see the power grid panel with all the parsed lines of the power grid hierarchically displayed of its metal layer. Then we have the configuration panel where we set the analysis options like the technology of the power grid line, the temperature, the width. We also have there the discretization of the line. Then after selecting a line, its geometric plot is automatically displayed in the top of the screen. So that the user can fully understand its geometry and all the segments that compose it. And after an analysis is performed, the corresponding plot is displayed in the middle of the screen. And finally, at the bottom, we have a space for message log and statistics of the analyzed power grid. Now, as for the toolbar, of course, we have the file menu with new, save, open, etc. things. Then we have the simulate menu, where the user can select the desired simulation and the simulation parameters. Then the plot menu in order to display previously run simulations, and the export menu for various reports and statistics. Overall, the user interface is rather intuitive and simple, or at least it was designed to be that, which further enhances the user experience by effectively encapsulating all the state-of-the-art methodologies and libraries in a simple and user-friendly way. Now, in addition to the aforementioned user interface, Proton also provides a command line version for a more automated run of electromigration analysis. It follows the same flow as mentioned in the previous slides, and which are organized and split into simple commands. Also, Proton offers the option to source TCL files, TCL scripts, that can be used to fully automate the electromigration analysis process so that it can be seamlessly integrated into any power grid design flow. Now, I encourage you to actually check out our tool and try it. You can find it on GitHub, the complete installation guides and detailed documentation. And actually, whether you are an academic researcher or a design engineer, we think that Proton can help you very much gain insight on the physics-based behavior of electromigration phenomena. And now, in order to conclude my presentation, let us take a step forward and think about chiplet-based designs. Now, chiplets bring unique challenges to electromigration analysis. The increased interconnect density and complexity can significantly impact reliability. And when introducing heterogeneous integration, we are faced with non-uniform stress profiles that are tough to predict. These issues are amplified for vertical interconnects like TSVs, microbumps that create stress hotspot. To adapt Proton for this evolving landscape, as we can say, the primary step is actually to extend the power grid line analysis to account for vertical interconnects in order to seamlessly build on the solid foundation 2D analysis. This way, we aim for a smooth transition between the 2D analysis that we are now into the 2.5 3D power grid analysis. Finally, and this is something that I believe very much, collaboration between the industry is actually the key here. Validating on real chiplet benchmarks will be crucial to tuning the simulation methodologies and gaining insights into practical deployment. And as the industry increasingly shifts towards 2.5 and 3D design flows, Proton's flexibility will make it an invaluable tool, we hope, in ensuring reliable chiplet-based systems. And of course, the ultimate goal here is to continue democratizing electromigration analysis and keeping everything as open source as we can, while staying ahead of emerging design challenges and thus bridging the gap between the traditional VLSI and the future of 3D integration. So, yes, that's it from me.
So let me ask a question to start also the process. So Anuj, I would like to ask, so I saw that you have this also soft error in 3D chiplets. Is it feasible to adapt CoMeT simulator also to consider like soft error reliability and see how this have these flip bits in the memory stacks?
So not off the shelf, but this is something on our agenda to in our roadmap to actually have this implemented, like to flip bits both in memory and in the processors using fault injections. This is an ongoing work. And we want to link it to the thermal. So hotter the particular part of the chip is, higher would be the probability of the fault injection being successful.
Okay. And actually one question to Alberto also. My question was how much is the manual of the engineer that has to create this higher 3D. So I saw that it has a lot of in-house and industrial tools. So is it easy to adapt from 2D directly to 3D integration based on this hard 3D flow? Or
yes, actually, I believe the key point is the fundamental ideas. Later on, the adaptation and implementation are not so complicated. So we have two levels. One is the level of the set of scripts which are required for the system, let's say, to the fundamental run. And this is relatively simple, and I believe it can be easily replicated. The other part is the additional algorithms which are required for the part of the floor planning. This part is a bit more critical, but with this exception, I believe the replication for other tools, for open source tools, is something that will be very interesting to do, and I believe hopefully will be one of our next steps.
Okay, thank you very much. So are there any other questions? Yes, I see. Thanasis, yes?
Yes, hello. First of all, thank every one of you for these presentations. They were informative. I would like to ask some things, some general things. My questions are not directed to some specific person. Alberto, Anu, and Olympia may all answer. My first question is, do you know why it seems that industry is a bit hesitant to adopt 3D for planning technologies in their tools? And the second one is those tools that were presented to us today, since they are planning or on making space for 2.5D or 3D chiplets, do they require significant more processing time, or do they have large computational requirements? These are the two questions.
Thank you, Thanasis. Maybe Anuj or Alberto or Olympia, everybody.
Maybe one part of the answer from my side. As far as I know, I believe the key players in terms of CAD, they are doing a huge investment and huge research in terms of algorithms for addressing 3D. The problem is that 3D, place and route, synthesis, and so on, is relatively easy when you consider simplified problems like sequential 2D, but it is extremely challenging when you address systems where you try to do chiplets analysis or multi-tier with heterogeneous. So I would not say that they are hesitating. I believe the point is that they are strongly researching in that area. And definitely, this will require to rethought a lot of the 2D tools that we have right now, because a lot of, let's say, the metrics, the cost function that we are using are inappropriate in this scenario. But probably, Olivia, the other colleagues have another opinion or...
Actually, I will mostly say the same as Alberto did, so you mostly covered me. But what I would say is that in general, what we see from the industry part is that industry is quite conservative. Academia moves faster into more new things, into newer things. So I think that they need to research, as Alberto said, more in order to trust the new things. So I think that we will most likely see this in the following years, but I think there is some time for the industry to go to this direction, to adopt them, and to be convinced to adopt them. So yes.
I see. Thank you very much. I don't know if Anuj has to add something else. Both of your answers make sense to me, actually. I know that there is a lot of research going on right now in academia, but I have not seen any, dedicated tools that goes end-to-end 3D floor planning. Perhaps it's what Olympia suggested. I'm not sure. I would also like to ask something else regarding the 3D. Some partners here showed us some simulators. On a general sense, does 3D integration impose several problems in terms of thermal power distribution of a grid to the point that it is almost impossible to achieve? Or are there some methods to efficiently dissipate heat? Because in my mind, when you design a 3D, not 2.5D, a 3D design, a 3D chiplet, let's say, the power dissipation is very hard to achieve, right? Like really hard.
Yeah, so I think one of the main reasons which stand in the way for the adoption of 3D technology is probably thermal. So, so as you said, heat and power dissipation is very difficult. So we don't have very good solutions for this from industry yet, but there have been solutions from in research that has been proposed that they use 3D microfluidic cooling, which runs along with TSVs, which are providing the communication between the chiplets. So there are exotic technologies to achieve this. So thermal is still an open problem to be solved, and 3D only makes it worse. So, and beside that, also regarding your last question, I think economics is also very important for industry. So it is not necessarily that something that has been shown to be a proof of concept will be adapted by the industry in the real world, because it has to be also produced financially viably and should scale, and the production should scale. So Intel did produce 3D chips. I think they came up with a based on Floros technology, they came up with a processor. I think it was called Alder Lake, maybe more than a decade ago. But the processor itself was so expensive that nobody wanted it. And it was only produced in a very limited production because of very limited yield. And of course, if a processor is produced in a very limited quantity, then the associated cost of manufacturing, maintenance, design, software support becomes all too much expensive for a particular design to continue. So these are some real world constraints which industry also has to take into account.
I see. Thank you, Anuj. Thank you very much for your answer.
Thank you. I think there's another question on the Q&A. Let me. So one question, I think, for the entire for all the speakers is: are you in the contact with any foundries to update relevant aging data for open source project, or is it pure physics model based?
I don't know if this goes to electromigration, to my talk, but I will answer. And of course, if any other speaker wants to answer, by all means. So foundries and in general industry, they are not very reluctant to give out results that they have done through experiments or on their models, designs, etc. It is quite difficult for the NDA, especially as you go to lower dimensions, to newer technology nodes, to process nodes, like 3 nanometer, 5 nanometer, the cutting edge. So it is quite difficult to obtain this. However, there have been some research done around it on how to tune these physics-based models for electromigration. And if I'm not mistaken, currently in the industry, some industrial partners are collaborating with academia in order to achieve this, and in order to get rid of Black's model, the mean time to failure Black's model that is currently used. So yes, for the model that I personally showed, we have not been in communication with any foundry, but this is the base, and one can take the model, a company can take the model and test them themselves and tune them in order to accurately use it. But also all the other speakers can speak for different research topics.
Yeah, so we work on a much higher level of abstraction than foundry. So the companies we talk to are basically computer architecture companies like Intel, AMD, NVIDIA, ARM. So again, here due to security reasons and proprietary reasons, they don't really, this data is generally don't release. So what you can do is that you can send, for example, we have shown our heat maps of our simulations to these executive under the companies, and under NDAs, they have kind of revealed that our heat maps are for the 3D processors are in the same ballpark figure they observe in their own labs. And I think, and they probably don't want to say anything more than this. So this is the contact we have. There is the risk of having too much contact with the industry under an NDA, because then you may have a lot of information, but you may reach a point where you can't publish anything based on that information, and it becomes complicated very fast.
Understandable. Thank you very much for your answers, both of you.
Thank you. Thank you all. So is there any other question? No. So I would like to thank you all the speakers and the participants. So we will upload the webinar also in our YouTube channel. So feel free to check it out when it is uploaded. So for that time, I would like also to conclude this webinar, and hope to see you in our next webinar also.